in the biological brain, there was an idea that was in vogue a few decades ago. It's fallen out of vogue a little bit now, but it was the idea that you would have like a grandmother brain cell that would fire when you saw your particular grandmother or heard her voice, that this, particular neuron would fire. And in subsequent years, it's become clear that, for something that complex, you don't just have one brain cell amongst the 90 billion in your brain that fires, but you have a set of brain cells, and those set of brain cells firing together gives you this representation of your grandmother. And so this seems similar, this kind of having a grandmother cell seems similar to something that you talk a lot about in your BDH paper, which is your discovery that there are specific neurons that fire for the idea of a currency or for the idea of a country. And the implication there is that it might be much easier with BDH to interpret what the neural network is processing than with a dense activation like a transformer-based architecture.
Definitely, and definitely this is true. The way to look at it, first of all, is again comes back to positive activations. One of the things to note about positive activations is that combinations are easy to express. You don't have to work so much with doing things like projections or finding like the right negative and positive coefficients to say that I want this part of my network to activate in a positive way and that one in a negative way and balance it all together. You have full interpretability because you just say, I want this set, I want this combination to fire, and then this represents my grandmother. Interestingly enough, if you dive into optimization of this type of architectures and find the natural patterns that they optimize for, there's a pattern that the more important concepts are represented by generally smaller sets. So for those in the audience who are familiar with concepts of network science, of systems, there's this general search for power laws in systems, power law distributions, in which the more important concepts are somehow more compactly represented. And you can actually, for the more important concepts, even in a relatively small network, even at like 100 million scale or even below that, find in our network an individual synapse which is sufficient evidence for a concept being mentioned. So this touches on a notion known as monosemanticity, or being responsible for one concept and triggering on one concept, and this we see. Perhaps one more thing, John, to say is when you mentioned the notion of grandmother cells and how they appear spontaneously. And in architecture, it's not architected. There's no like genetic code that says, hey, I want to have cells responsible for different operations. They evolve, they emerge in the course of training. We have no control over where they will be, but we find that they emerge and that you have this very clear location of signals signals passing through the artificial brain as a function of what we're talking about.
Right, so kind of like your multicolored Tower of Macaron, you don't have control over where kind of the orange and yellow Macaron end up in the tower, but you can bet that they will kind of end up aggregating together somewhere in the structure. You just don't know where.
Yeah, it's pretty fascinating. And as we continue with this tower and it becomes sparser, you also end up with patterns in which the most important kind of locations are filled. So those more important concepts are filled and the less important ones are not that much filled. Maybe one thing to say for the audience who's kind of interested in technical details, there's one fascinating technical detail here, is that in our model, what we've been able to find and what actually sheds some light on how these things work, is the concept of a grandmother synapse rather than a grandmother neuron. Which means that if you think of how the state of the system works, the state of the system, the context that we are listening to, is represented by synapse activation, potentiation, and those synapses that are responsible or that are related to specific contexts activate in those settings. So we have specific synapses which react to specific notions.